So we have a generic reaction. Okay, our regular form that we've seen several times now, we have, let's say for sort of ease and familiarity, we have A and B as reactants, and we're forming C and D as products. What are our lowercase letters indicative of? What are these things? It's real mumbly. Someone say it confidently. Stoichiometric coefficients. Okay? So these are essential to balancing our reactions and making sure we have whole numbers of moles. Okay? And again, like I said, for now we're just focusing on forward reactions. Okay? So in that particular case, we can define the rate of reaction as how fast the concentration of a reactant or product is changing with time. So reaction rate, and we can write this, let's say we write it for, with respect to the concentration of A. So for our sort of differential form, our instantaneous rate of change, we have dA, d concentration of A, dt, okay, with respect to time. I'm going to put a negative here, and I'm also going to put my lowercase alpha in the bottom. Or alpha, it's just an A, okay? I hope today goes better, but this lecture last semester was arguably the worst one of the entire semester. I said nothing correctly. There were elaborate announcements on Canvas fixing all my errors. So hopefully it goes better this time around. So why have I put a negative here? Yes?
We're losing that reaction because
we're only talking about the forward reaction, so A is decreasing with time in this case, all right? We have a negative because A, as one of the reactants, is disappearing. Okay, we're only considering the forward case. Okay? And we've divided by our coefficient, okay? So we divide by our coefficient because we want to be able to write an overall reaction rate that is the same regardless of which species we decide to track, okay? So if we track A as it disappears, or we track B as it disappears, or we track the appearance of C and the appearance of D, we want to be able to write an overall rate that would be the same regardless, okay? So we want to be able to define rate in a way that doesn't matter, like I said, which species of the reaction we follow. Okay. So I'm interested then in, I could track the disappearance of the concentration of B's going down with time. Okay. I can set this overall reaction. This is now, I no longer have a negative because I'm making C, and I would be making my product D. Okay, so the positive here is, again, the reaction rate could be for the appearance of product C. Okay. So I said this form, our differential form here, is for an instantaneous rate. And we'll talk about that a little bit more. I have some, I don't know if anyone looked at the slides for this lecture last semester. I just pulled them all from some random website. I did cite it, and I was like, these are all basically from here. It's some like really ugly clip art on them, and I just left them that way. I've fixed some of them for this semester, but not all. So there's some improvements, and we will talk about instantaneous rate versus an average rate or an initial rate with a slide in a moment. But so this is sort of represents our instantaneous rate. We could also talk about sort of an average rate or an overall rate, and we might see sort of our big deltas here. Okay, we're actually talking about between two time points, between two measurable concentrations, we're taking subtraction, as opposed to we have some sort of curve, and for an instantaneous rate, we're going to pick a point on that curve, an instantaneous time point, and take the slope of the line tangent to that point. Okay, a little bit different. So we can plot concentration versus time and look at what those plots would look like. So if we have time here, most likely in seconds, and we have concentration here, and let's have an even more simplified reaction. Let's just have A going to B. Okay. So we'll have a curve for A that looks something like this. Okay. A is decreasing with time. Maybe the curve looks like this. And we start with approximately 0 B, okay, and we're forming B. So we can pick a time point somewhere like this. And like I said, if you draw a line tangent to your curve and take the slope of that tangent line, you have instantaneous rate, okay, slope of the tangent equal to dB dt. Okay? It's positive because I'm making B. I don't have anything at the bottom because I already wrote that I have a 1 for my coefficient. Okay, and then here, my drawings aren't going to be great, but go ahead and imagine that the slope here, dB dt, is negative dA dt. Okay? Equal and opposite. Now I could also have then, alternatively, if I have the equation A going to 2B. Okay. Now what I have is I'm still starting with approximately 0 product. And here's my curve for making B, okay, whatever this concentration is. And I'm starting with about half as much A. So this curve looks something like this. And so now, if I go and pick some time point, okay, again, I have a rate for the appearance of B, and I have a rate for the disappearance of A. And these ones should look, the slope should look a little bit different if I could draw. But, so sort of the instantaneous disappearance of A at this point would be equal to, it kind of looks like half dB dt. Okay, and then this is, of course, my stoichiometric coefficient. So, like I said, we're not covering much of this chapter, and that's okay. We're not going to get into anything beyond this. Chapter 17 spends a lot of time talking about diffusion and transport and talks about more details on rates as a function of sort of the collision of molecules. But I said I think it makes sense for people, even without that part, that as concentration goes up, you're going to increase the number of collisions, and so you're also going to be able to increase the rate at which you would form product. Okay, and so we could sort of draw, if you had sort of, you know, beakers with the same volume here, and you had A molecules and B molecules, and let's say these two are going to combine to form C, okay? And then you put in twice as much over here, but you haven't changed the, you know, overall volume. Then you're going to make A plus B, creating product C, faster. Right? And this is related to sort of the probability of A times the probability of B. If this is sort of probability of being in adjacent lattice sites, means you can react with each other. Then this is proportional to concentration. As the concentration goes up, the probability of them being next to each other is going to go up. The probability that they can then interact and form product also goes up. The rate of reaction and concentration of your reactants are proportional through a constant. There's some proportionality constant, and we're going to call it the rate constant. And rate constant is going to be given by a lowercase k. I don't know how to make that look different than my capital K's for equilibrium constant.